I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on reflection of light interaction at a boundary. In this series of videos, we're going to talk about geometric optics, which is reflection and refraction of light. We're going to talk about reflection of light in this video, which is light interacting at a boundary. So what happens when light hits a boundary? First off, we know light travels in a straight line path until it reaches that boundary. So let's say we've got a piece of glass here. And when it reaches the boundary, it does several things. One of the things that it does is it reflects. It also can pass into the new medium, which is called a transmission. And it can also partially do both of these things. Now, a third thing that it can do, if the energy of the light is correct, then it can be absorbed into the medium. Now, in this video, we're going to talk about just the reflection of light. So reflection of light, and we're going to need to know some vocabulary. So the ray of light that's traveling towards the boundary is called the incident ray of light. So you're going to draw a ray of light that heads towards the boundary, and that's our incident ray. The ray that bounces off is called the reflected ray. Now, an imaginary line we're going to draw that is perpendicular to the surface is called the normal line. Remember the word normal, like normal force, is perpendicular. Now the angle between the normal and the incident ray is called the incident angle, and we're going to denote that with a θ1. And the angle between the reflected ray and the normal is called θ2. Now this is known as regular reflection or specular reflection, where θ1 is going to equal θ2. So those two angles from the normal line are going to be equal. Now if we wanted to locate an image, so let's look at a mirror that's hanging on a wall. The left side of the mirror is the room. The right side of the mirror is what would be seen in the reflection. So if we take a person standing in front of that full-length mirror, and we want to locate the image of that person, there are countless rays of light that are reflecting off of this person and hitting the mirror from any part on that person. So what we're going to do is we're going to just pick one spot on the person. The easiest spot is the top of the person, and we're going to draw a ray of light, our incident ray of light, hitting the mirror, draw the normal line, and then we'll draw the reflected ray. Now, in order to locate the image, we know that the image is going to form on the right side of the mirror, the reflected side. So what we're going to do is we're going to take that reflected ray and we're going to extend it back into the mirror using a dashed line. Now what this represents is the ray of light that we would see that actually appears to travel in a straight line for our eye. Now in order to locate an image, we're going to draw another ray of light that does the same thing. And we could draw it anywhere on the mirror. As long as it hits the mirror and reflects off, then we can extend the ray back. So the easiest ray of light that we can draw is the one that travels parallel to the surface, because it's going to hit the mirror and it's going to bounce straight back at the top of the hat. So we can extend this ray back, and where those two rays intersect, the dashed lines intersect, remember those aren't actual rays of light, which is why we draw them as dashed lines. Where those two rays intersect is where we're going to see the top of the hat, and we can actually draw the entire person as a reflection as well. So we could repeat this process over and over again for different parts of the person, and we would find that the rays of light would all intersect at the exact location of our image that we can see in the mirror. Now the distance that the person is standing in front of the mirror, that distance is known as the object distance, which is denoted with a lowercase s and with a subscript of O. Now the object standing in front of the mirror also has a reflection, and that reflection is that distance from the mirror is called the image distance, which is denoted with a lowercase s and a subscript of I. And the object distance is equal to the image distance for what's known as a plane mirror, so a mirror doesn't have any curvature to it. So the object distance, how far you are in front of the mirror, is how far you appear into the mirror. So the question that naturally is asked is, why do we measure from the normal? Well, the incident angle and reflected angle are measured from the normal because not all surfaces are flat. So let's take a piece of water that is kind of choppy. So we've got some waves, and we draw a ray of light. And if we were to measure that angle from the surface, call that theta A, when it bounces off and we have theta B, we can see that those angles aren't going to be equal because the surface is not flat. So the reason that we measure our angles from the normal is we can draw that normal line, and those angles, theta 1 and theta 2, the incident angle and reflected angle, will always be equal in relationship to the normal line. So that's why we use the normal line in order to measure our angles of incidence and our angles of reflection. We have several different reflection types. So specular reflection is what you see when you're looking into a pond. So this is what this person would see, is we have the tree that is on one side of the lake, and we see a reflection in the water of that tree. And the reason that we see that on a nice smooth surface for a lake is we can draw a ray diagram to explain. So if you take a ray of light and drawing it from the top of the tree, it's going to hit the lake and it's going to reflect off into the person's eye. And we know that the incident angle is going to equal the reflected angle. So we can extend that reflected ray back, and that's where the person is going to see the image of the tree in the lake. So it looks like that the tree is inverted. So the specular reflection is rays of light reflecting off of smooth surfaces, causing an image to form. So like the lake that you'd see outside in our school. Now diffuse reflection is different, which is what helps us see most things. So if you take two rays of light from the same spot and now the lake is choppy, and let's say there's a strong wind that's blowing and there's a little bit of waves, those rays of light are going to reflect in different directions. So they're going to diffuse and go in different directions. So we're not going to see that image that forms of that tree because the rays of light aren't going to all concentrate and reflect. So that happens off of a rough surface, causing the rays of light to reflect in multiple directions. Now a rough surface could seem very smooth, but in the case of a table which seems smooth, it's not smooth. It has, at the microscopic level, has very rough edges, and that's what causes diffuse reflection. So the nature of seeing. So what happens is we have light comes from a source, so the sun, a light bulb, candle, campfire, etc., something that produces light. Then light is absorbed and then reflected in terms of diffuse reflection from those objects. So then the reflected rays enter our eye and form an image on our retina, and then our brain interprets that image. So in order for us to be able to see things, light has to enter our eye. So let's look at a picture of a street, and we can see that the reason we can see this cab is light hits that, diffuse reflection occurs, and it enters anybody's eye that is standing anywhere on that street. So as long as you're in a straight line path with the cab, you'll be able to see that cab. Now, the same thing occurs with this building. The building, you can see the red brick because the light is absorbed and then reflected, and you see the color that you see is what is reflected off of the building. So when you look at the American flag, when you see the red, white, and blue, what's happening is that the light that is absorbed into the flag reflects off, and that's the color that you see. So the colors that are reflected off are the colors that you see. Now we also have several light sources in this image. You can see the oncoming traffic. We have the headlights. The walk sign for the crosswalk is a light source, and the buildings as well. And the reason we can see all of those buildings is because of the sunlight that reflects off of the buildings. So this is an introduction to reflection of light. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below, subscribe to my channel, Cavi Coaches, and follow me on Instagram and X @CaviCoaches.